Okay, thanks. So yes, we'll start the session with a bit more another story from the chemistry that you can do in muons. And in this case, looking at reaction kinetics, which was one of the areas Ian highlighted on Saturday. And we'll be looking at rates of H abstraction in the alkanes. So just an outline of the talk. I'll start with a recap of some of the things we've looked at earlier in the school, and then I'll go on to talk about why we're interested in studying alkane abstraction reactions, and then we'll go on and look at the new measurements we've done for propane, and I'll tell you the story up to the point where we've got to in the study. So just starting with a few acknowledgements. The person who had a good idea of doing radio frequency measurements and measuring these reaction kinetics was Don Fleming. And Ian, who you met on Saturday, and Jamie also worked a lot on the experiments. And behind us there's a big team at ISIS making all the gas cells that you'll see as we go through the talk. So starting with a recap, and I think all this comes from the chemistry lecture and the pulse techniques lectures that you saw on Saturday. So firstly, muons, well, we're going to, as always, stop at being positive muons in the sample. And for these experiments, we're pretty much only interested in the fraction that forms this muonium atom, this bound muon electron state. And we're going to be doing chemistry, as I said. So the whole point is that muonium is chemically equivalent to the hydrogen atom. There'd be really no point in doing it if that wasn't true. And the reason for doing it is that it greatly extends our isotopic mass comparison. So as I think Ian said, you've got a ratio of 1 to 9 with the hydrogen, and 1 to 18 with deuterium. So it really gives you quite a considerable boost when you come to look at isotopic comparisons. And pretty much the only reaction, of course, as Ian said, when you've got muonium atom, it can undergo all the reactions that hydrogen atoms would do. But for this talk, we're mainly considering the abstraction reaction. So that's the chemistry. So as Ian talked a little bit about how we might go about measuring muonium formed in a sample. So in this case, we're implanting muons in the sample, and we put on a small transverse field, transverse to the beam polarization. In this case, it will be about 2 Gauss. The energy level diagram for the muonium system is given by this bright light diagram, which you've seen before. And so if at low fields, at about 2 Gauss, muon 2 and 2,3 are degenerate, and the precession frequency of the muonium will be about 2.8 megahertz. So when you actually make this measurement in your forward backward counters, you'll see this oscillating signal. And much of the kinetics information, or all the kinetics information, can be obtained by looking at the decay of this signal. And then also part of this talk will involve RF measurements. So these you saw on Saturday in the pulse techniques talk. So in this case, we're still implanting the muons, but now we're implanting them along a large static field of the order of a kilogauss. And then we're going to switch on a radio frequency signal perpendicular to the muon polarization, perpendicular to the static field. And we'll time that RF excitation relative to the muon pulse. And the experiment will run by sweeping the strength of the static field through this resonance condition given by the London condition. Then Ian talked a little bit about kinetics measurements, so I just repeated one example for the addition of muonium to a phenol ring to form this radical state. So if we look at phenol solutions in water, If you measure pure water, you get a long-lived muonium signal, and that's effectively your lambda zero for your experiment. And then as you add in phenol into the mix, into the water, the damping grows, and as you increase the concentration, the damping grows still further. So you can measure these relaxation times and then plot them as a function of phenol concentration for a particular temperature, and then fit all that with the first order rate equation to extract Ku for that reaction. And then you can follow Ku with temperature. Again, this is a picture that Ian showed. You can follow Ku with temperature to get the activation energy for the reaction. So in the course of this talk, we'll be going all through this process. So moving on to why we might be interested in studying alkane abstraction reactions. So fundamentally, it's a way of testing reaction theory, reaction rate theory. So people are interested in being able to calculate reaction rates and calculate whether reactions will happen. And to test their calculations, they need simple systems to benchmark them against. So that's very much why we're doing these measurements. And actually, I went to a gas kinetics conference, and someone who had no muon experience started very early in this talk talking about muonium as an isotopic comparison. So that was good to hear. So we're going to study muonium abstraction rates across the homologous series. So we're going to be looking at we'll be looking at propane, but previously people have looked at methane and ethane and so forth in the series. And we're going to be looking at the kind of kinetic isotope effects, so we're going to be looking along the series, but also looking to compare the measurements we made with muonium with work previously reported with H and D abstraction. So looking at the homologous series, so people have previously measured muonium abstraction in methane and ethane, and obtained activation energies for these two systems. I think they're expecting them to be closer together since they've got the same functional groups and similar chemical properties. And so there was a surprise that ethane was much lower as it was compared to methane. And then looking at the isotope comparison, so I've got a picture of methane here. So we've got the activation line for muonium abstraction and hydrogen abstraction. So you can see there's the activation energy is considerably larger for muonium than it is for hydrogen. And if you look at the difference for methane and ethane, for ethane, you get just over 6 kilocalories per mole as the activation energy. For methane, it's about 11. So the difference for methane is in line with what you'd expect the difference to be from arguments the muon 0 point energy. But the difference for methane is much larger than expected. So what I'm trying to say is there's unexplained things happening in both the reactions along the homologous series and also in the isotope comparison. So it's something people can computationally get their teeth into. So there's a clear interest, since we've looked at methane and ethane, in extending the study to the higher mass alkanes, and also continuing to look at the isotope comparison. So really, if we've looked at methane and ethane, the next step is to look at propane, the next one in the series. But this was thought to be a very slow reaction, so we expected it to be extremely difficult to measure using the TF measurements that I talked about earlier with phenol. So the objective is to measure the kinetics for this reaction. So muonium will abstract to hydrogen from propane to form this mu-H species and leave this. So we're starting off with muonium, which is a paramagnetic species, and we're going to end up with mu-H, which is the dimagnetic state. So you can see there's a change of spin state for the muon-containing species. So the muonium precursor, muon reactant, is paramagnetic, and this is dimagnetic, so they're spectroscopically distinct in our measurements. So we can either measure lambda mu for the disappearance of this muonium state as the reaction proceeds. But it's going to be a slow reaction, as I said, or we think it's a slow reaction. So lambda mu, the values of lambda mu we're likely to be measuring are going to be of the same order as the lambda zero for the system. So that could be difficult, could be almost impossible. The alternative, which Don suggested, was to try a new technique. And in this case, rather than measuring the disappearance of muonium, would be to measure the appearance of this mu-H species. And we can do that using RF in an experiment very similar to NMR. And because the muons are being implanted along this large static field, the problem of lambda zero goes away. It's not an issue because the large field has good field homogeneity. So the hypothesis was that this RF technique might be a very good way of actually measuring slow reactions. So just digressing a little bit to the experimental setup, the experiment requirements make it pretty tough to do this measurement. So we want to work at 50 bar, but we're using a surface muon beam, so we've got to get muons in through a thin window into the gas sample. Stopping muons in a gas, even at 50 bar, is going to leave an extended path, so we've got to have quite a long cell to stop the muons in the sample region. And to get the activation energy, we've got to allow for variable temperature measurements, and we aimed in designing the kit to go from about -50 Celsius up to 250 Celsius. And as I was saying, we were hoping to do some resonance experiments, so we need a resonant cavity in the kit. So we came up with the final design was a 46 centimetre long, 3.5 centimetre diameter cell with 150 micron titanium window on the end, which you can see there. And the temperature of the gas is controlled by circulating oil through a jacket around the gas sample. Now the problem is, when we started with these measurements, we started with the idea of making plastic cells so that we could mount the RF coil on the outside of the cell and the RF field would penetrate into the sample. Unfortunately, many plastics, we found out gas impurities into the gas sample and actually changed the chemistry that we were trying to look at. So we spent fruitless, 6 months perhaps, doing experiments that gave us null results. So in the end, we accepted we had to use a stainless steel cell from the point of view of keeping the sample clean, and so that the RF coil had to be inside the cell to allow us to do the resonance measurement. So the geometry of the kit is we've got the cell, the long cell, and we've got the beam coming into the window on the end of the cell. We've got a field applied collinear with the muon beam. And then, as I said, inside the cell, we've made an RF coil, which you can see in this picture down here, which is a very simple saddle coil with, I think, 4 turns on it. But those of you who've done NMR will know this coil is about the size that you could put a mouse into. So we're trying to do essentially solid-state NMR with a coil that you might more typically use for imaging. Except in how we managed to get it to work. So this coil ends up tuning and matching in the experiment to just over 9 megahertz. So we're going to be, in the next set of measurements I'll show, we're going to be doing RF measurements. So as I said, we're implanting the muon beam along the static field, and we're applying a radio frequency field timed to the muon pulse. And as I said, we'll be looking at the resonance we'll be finding the resonance condition, but all the measurements I show will be made at resonance, looking at the time domain signal at resonance, with the RF on throughout the data taking. So as I said, I think on Saturday, what we're seeing here is the precession of the muons around the RF field that's being applied. So the RF coil, for most of the experiments, I think, is tuned to just over 9 megahertz, and we've got RF pulses of about 32 microseconds in duration, which is equal to the data-taking window at I6. I think if you fit this data, you're going to feel RF field P1 of about 6 Gauss. So as I said, we're interested in measuring the product state, UH. So what we're doing is loading propane into our cell. Now, what we want to do is to vary the concentration of propane. So we're putting propane in and then using a nitrogen buffer, nitrogen gas buffer, so that we maintain a constant stopping distribution. And for these measurements, it's important we maintain the distribution inside the RF coil. So we're having to check that the gas density is always equivalent, so that we stop the muons inside the coil so that they experience the RF field. So you can see here for 0.8 bar, so a very low propane concentration, the at-resonance signal is fairly small. And that's because with low propane concentration, we expect a very slow UH dimagnetic final state formation. If we increase the propane concentration, or 0.5 bar, we see a much larger increase in the signal. We see the signal developing. And we attribute that to clear UH formation system. So the next challenge is to actually fit those signals. And unfortunately, an expression for the signal in an RF experiment with state conversion was actually previously worked out by Morozumi et al. So what we're doing is we're measuring this dimagnetic signal with our RF in the experiment, and then we fit all this lot to the data, to the data we're getting from the RF measurement. And then from that, we can extract the kinetics data, this lambda mu parameter that we're going to plot to get the value of k mu. Something we perhaps hadn't thought through enough was that there are actually rather a lot of parameters in that expression. And each of those is a possible source of error in the measurement. So we spent a lot of time doing calibration measurements to minimize that, but it is in the end a concern with the technique that you've got to establish these fairly well and decide which ones need to be fixed to get good values from the measurement. But we worked all that through, and we carried out a series of measurements at different propane partial pressures, and got a nice set of values for lambda mu that fell on the straight line that we were trying to fit to for this first order base equation. So we were able to fit that with this, and from that we were able to extract a value of k mu, the rate constant for this measurement. And that's all was done at 300K with this RF experiment. And the first thing we noticed was, well, we got values about 7 times 10 to the minus 16. The first thing we noticed was it was about 3 orders of magnitude faster than we were expecting, or certainly Don was expecting from previous measurements. So the thing is, if it's this fast, if it's 3 orders of magnitude faster than we were expecting, we should be able to make a direct measurement looking at the disappearance in muonium. It should be possible for the system. And the reason why you might want to do that is a much simpler experiment. So we could dispense with all the RF kit, all the difficulties of establishing these parameters, and just simply look at, in a small transverse field, the disappearance of the muonium signal. So we're going back to TF and USR. So we're applying a small, in this case, 2 Gauss signal, and we're going to get the kinetics data from the envelope of this data, this processing signal. So we went back and measured, carried on the work in propane, but this time looking at these two gas measurements, spin rotation measurements, and we made measurements of lambda versus pressure across a wide temperature range, and we ended up with an activation energy along defines the activation energy for propane. A set of points, and you can see immediately that it's much smaller activation energy than for the case of H plus propane, which is shown by the red line. And the good news was that our previous point, which had been made with the RF data before we set out moved to making TF measurements, felt pretty near the line that we got from the TF measurements. I think there was an error of about 30%. So that was very good news, particularly if we published that this time. But the thing that struck us was that the activation energy was very small. Very small. So what we were now looking for was an explanation for that. So summarising what we've done, we started out by following the formation of the muH product using RF techniques. We obtained a single value for K mu of 300K, and then we noticed it was much faster than we were anticipating. So we continued the study looking at the disappearance in neodymium using the more conventional TF neuroscience, much simpler experiment to do. And then we've ended up with a set of activation energy for propane. So what do the results tell us so far? So the conclusions so far, and we're still working on this, well, as I said, the rate constant at 300K was surprisingly fast, 3 orders of magnitude faster than we expected. And the TF measurements confirm that, and I think we've since found other data that confirms that, so it all ties together. And so we'd expect a small activation energy for the system, which indeed we do measure. The TF measurements show the activation energy to be very small. It's actually about a tenth the value of ethane. In classical transition state theory suggests that the isotopic comparison would be about 1 to 1,000 for Kmu to Kh, but actually we only get about 1 to 3. So the results suggest to us that there's a large and unexpected contribution from quantum tunneling in the system in this mu plus propane reaction. So I think that's where I stop and say at this point we need some help from the computational chemists. So as always, we've done some experiments and now we need some computational help to understand. Thank you.
Questions? So, can you explain, hand waving, what is the rationale between the difference of activation energy across the homologous series? So why do you expect?
Well, it's the same functional groups in the system, so we'd expect.
So why should the reaction become so slow in your long?
Well, no, it's slow because of the measurements previously. We thought it would be slow because of the measurements made up previously on methane and ethane.
Yeah.
Those measurements, those measurements were all made at very high temperatures. So they were all TF2 gas measurements, but they were made at many hundreds of Kelvin, very high temperatures. So at 300 Kelvin, we would expect where we wanted to work for propane. We would expect Kmu to be extremely slow. So that was the simple reason. It was the temperature we were working at in these measurements.
So I'm a little confused by something. You said for your RF coil you use a mouse-sized RF coil, but you also said, because since you're using gas, you needed like a 0.5 meter sample environment.
Yeah, that's right. So we came up with I guess the simple answer is we don't need that length for this measurement, but some other measurements worked at much lower pressures, so the path length will be greatly extended through the gas. Okay. So if you're not making RF measurements, you can use the whole length of your tube.
Right.
And take the data, so we have done other measurements that use that. But if you're going to do an RF measurement, you've got to stop all your muons in this sample coil, in this RF coil.
Right.
Otherwise, the RF will have no effect on the muons.
Okay.
And to do that, you need to move to higher pressures. So the last 43 centimeters of your tube isn't being used in this, case. Yeah.
More questions? I have one, because I have no clue about gases and chemistry. In your reaction kinetics, what is the time it needs that the muon actually gets to the molecule if you have low partial pressure?
It's still quite fast.
It's still quite
fast. Yes, it's still quite fast. But with the RF, it's not that important because you're implanting a collinear with the static fields, so then it's really when the RF starts acting on you. But it's still quite fast.
Okay.
No more questions?
Just one quick one. Then you mentioned in the end that you may think that quantum tunneling is the answer. Isn't it strange that, I mean, I would think quantum tunneling requires that the hydrogen level is the same in the starting and final environment. So that, isn't it strange that the bigger molecule is more akin to OH than...
No, I think that's right. It is strange, and that's the puzzle. That's why we were surprised, I think.
Okay, I think we have to proceed. So thanks, Stephen.